Now, so what I want to just do for the last few minutes here is show you some of the pictures of data we get, just some of the movies. These are all, some of them are sped up a little. This movie represents 20 minutes of viewing time, and it's a lot shorter than that. You're not going to have to sit here and watch 20 minutes of the movie. Some of them are real time. Tom, if you could just give me the cursor. So what you want to look for in this, okay, you might be able to see a dust particle here. This is that inner disk that rotates at the beginning. Because at the beginning, it's a solid. Okay? And what does that mean? That means as I try and move it, the forces go up in proportion to how far I move it. Those increasing forces move the inner cylinder. Okay? Eventually, the bubbles are stretching. They can't stretch anymore. It's got to flow. And what you'll see is bubbles rearranging. Okay? And that's pretty obvious there. And then the thing in the middle just sits there and oscillates. It's oscillating because now the force is staying on average constant, but it's fluctuating around as the bubbles move. And we're in our fluid state. Okay? And one of the things to notice initially is if I stop it there, and you look at the bubbles, and I start it again and I stop it there, and you look at the bubbles, there's no obvious difference. Okay? So if I look just at a single snapshot in time, you can't tell the difference between the fact that it's now a solid and now a fluid. If I had stopped my videos of the molecular solid and fluid, and they weren't jiggling, you still could have all told me which was the solid and which was the fluid, because the one was more crystalline and the other was disordered. Okay? So we can't go by that usual thing anymore. So we need a new way of looking at it. Just to show you, we do more than just take pictures. This is a graph of the stress, which is that force on that inner piece, as a function of time, which is really just how far we've moved the thing, because we're moving it at a constant rate. Just to show you, we do get regions where it's basically linear. Notice here it starts wiggling a little, then it wiggles a lot. This one goes linear, and then it wiggles a lot. Okay? And I mentioned earlier, and this is my only other mention of it, the fluctuations. Okay? We want to understand the fluctuations. We maybe want to understand these little fluctuations before it gets here. These are a lot of the things we want to get at. If you look at these fluctuations, you can ask, is that a lot like what might happen in a real fluid? We can actually measure these much better. In a real fluid, you have many, many more atoms and molecules, obviously, than we have bubbles. We have maybe 1,000 or 10,000. Okay. That gives us another actually interesting question, which is how few bubbles do we need, or how many, to make it act like what we call a continuum? Turns out it's maybe 15 for those who care. Okay. We also, as I said, oscillate. So this is an apparatus where this arm oscillates back and forth. The bubbles sit here and we take pictures. We also sometimes want, I said in fluids, it's the velocity difference that causes forces. So sometimes you want a bubble that's not moving, but has a velocity difference across it. So the way you do that is you move one wall this way, the other wall this way. In the middle, they don't move, but they have a velocity difference. It's moving this way, and so there's a difference. So we do that with this apparatus where these walls move in opposite directions. You can see it's all very, very high-tech stuff that we actually just build ourselves, which is a lot of fun. Okay, so this is another one. I need the cursor back, Tom. In fluids, you get diffusion. So this might be a little hard to see. There's a yellow dot, a blue dot, and a green dot. And as the movie goes, what we're doing is we're tracking a bubble. Okay, so the bubble in the middle has no net velocity, but you see it's doing something that we commonly talk about in fluids. It's diffusing. Right? If you put a little dust particle in a fluid, it'll bounce around because the molecules hit it. The other bubbles are rearranging and hitting it, and it's got some nice random walk. These have a net velocity, but they're also diffusing. They're not going in a nice straight line. Okay? We can measure the properties of this diffusion, and we can compare it to what you would get in a molecular system. And there are differences. It's not exactly the same as molecular diffusion. So that's another way we can probe the system and ask what's going on. I mentioned oscillations. Okay, so here, this is a very slow frequency. This is actually real time. And what you want to do, it's a short movie, unfortunately, is watch the bubbles. And you can see that pretty much when every bubble is moving to the left, every bubble moves to the left. And when they're moving to the right, we all move to the right. That's what we call in phase. We're all going together. That's what a solid does. Okay? So at that low frequency, we're a solid. And then over here, we go much faster. And your eye should pick up kind of an S wiggle. Okay? We are what we call out of phase. We're not all moving together. This is what a fluid does. Okay? And notice we cause this transition not by changing the temperature, not by changing the pressure, but by changing the frequency that we oscillate. Okay? Is this a real phase transition, or is this just what we call the rheology of the material? This is just what it does, and there's no deep principles here. What I like about my research is we're actually asking the question, is there a deep principle? We don't even know the answer to that, never mind what the deep principle is. And that kind of makes it fun and challenging. And then the final thing, and I need the cursor back. Good thing we have someone in the back, is what we call reversibility of events. So we've started to look down at what we consider the particles, which are the individual bubbles. And this ability to oscillate things is something that we actually started in our lab. We were very excited to do because we could look at what we call in the field T1 events. So you see I've got the bubbles labeled by color. Black and red are neighbors, then they're not, and these are neighbors, then they're not, and these are neighbors. This is called a T1 event. It just stands for topological transition of type 1. That's all it means. I just think T1 is just as informative as that long name. And what this is a case where it reverses. It just, as you oscillate, it just keeps going back and forth. Okay? Reversible things are events you expect to happen in solids. They're elastic. If you stretch them a little and let go, they go back. Fluids, you don't so much expect reversible events. Okay? However, people, when they talk about foams, say T1 events are what cause flow. So we have this interesting regime where it's doing the T1 events, which are supposedly the flow, but they're reversible. So, what are we really seeing at that transition as we go from solid to fluid? Why are we in this regime where we have T1 events, but they're reversible? And just here is an example of what we would consider irreversible. They're not doing anything, they're not doing anything, and then you start to notice the bubbles around do stuff. And what we say is the energy landscape has changed. These bubbles are no longer happy because of everything their neighbors did, and it's a collective phenomena. Okay? And in condensed matter, that's what we like to look at, how large things all act together and behave in a collective way. And the nature of the system changed. It did its T1 event. We'll just show the movie one more time. And then it's happy in its new state. Okay? And maybe that's more indicative of really the flowing state, when you get these large collective events and they're all working together. So you could have the regime where you have these isolated, localized events that don't do anything, and you really need collective group behavior to get the fluid. And this gets back to that idea of fluctuations. You really need all the cars jamming before you're jammed, not just a few fluctuating in and out. Okay? So we really get at these transitions. So I'd just like to end with a few acknowledgments. This work, I should just say, has been funded in the past by DOE, and I really have to thank UCI for keeping it going when other people wouldn't. And for the online course, here UCI Extension really did a lot of help and work getting that going. These, I listed specifically the postdocs and students that have worked on foam that I could remember. I hope I didn't miss anyone. But I didn't put on here, I have to thank Tom, my grad student who's been working the computer. He works in the other area of my lab, which is more biophysics and Langmuir monolayers and membranes. So I didn't put him on the foam slide, but I do have to thank him for working the cursor. And I'd like to thank all of you for your attention, and I think there is time for questions.